Cool. So this is going to be a very informal presentation. I was going to prepare this for something else and then just transition it here. So this is a talk about, firstly, the current framework of understanding interpretable machine learning. Secondly, some existing techniques. These are not all of them because there are at least one or two popular techniques that I've intentionally left out, because I feel like they have enough resources for you to be able to learn about them on your own. I will mention them when I come to it. And then thirdly, this is more about like motivating project ideas, in terms of what can you do on your local machines without like need for infinite compute resources. So okay, with that we can start with this idea of interpretable machine learning. So the first question you want to ask yourself is like, what is interpretability? Because everyone has their own definition for it. And really, like everyone defines it in so many different ways with one common theme. The Oxford Dictionary definition of interpreting a particular interpretation. So interpretation basically means explainable. When it comes to explainable, we treat explanations as good if they are intuitive to communicate to humans. And a couple of papers go much deeper and they say interpretable means the knowledge that it distills has to be relevant, and this knowledge has to be used as insight for another expert to make a decision about a particular problem. But I don't want to go that deep. Explanation is fine, interpreting is explaining. And particularly explaining for humans pertains to questions of how. And more importantly, once you start asking how, you very quickly end up with questions of why. So how does a model make these decisions? Well, why did it make that decision particularly? Those kinds of questions crop up, and a lot of times in machine learning, it's not easy to answer them. So um, answering like what really like what is the property of good explanation as explained in a bunch of papers. The summary of it is like you wanted to match your priors, and priors is like your prior understanding of a problem before you see any data related to it. So if I see onions and milk, they will not likely make good chocolate. That is a prior. I don't know that that is the case, but I assume that that is the case based on my knowledge of chocolate. um so you really wanted to match your priors. Like if there's a car going off a cliff, you are likely to think this car will probably break or people inside the car will get hurt. And you want your model predictions to sort of match them, but not to the extent that you just have confirmation bias everywhere. Confirmation bias is like just believing what you want to believe before the problem, even after the data shows you something that might be different. uh, sort of. But yeah, that's one property. Another is like your explanations need to be social. People from layman to experts should be able to understand those explanations. General and probable is straightforward. Selected or MCQ. So it turns out what humans believe are good explanations. And this was conducted by like a survey of a bunch of people, asking them what a good explanation means to you. And they said we want options. Like an explanation should be, it should be possible for us to give a model like 5 options for explanation, and the model picks the an explanation out of these things. And last but definitely not the least, you want your explanations to be truthful. So when you're trying to uh, get to like these properties, you want to step back a second and ask, wait, but like why do I really need interpretability? Why do I need these explanations? When it comes to machine learning, aren't predictions like more important in the sense like, if I'm predicting well, do I really need to know why? Well, in a lot of cases you do, because sheep happens. And sheep happens is this I bomb. By I bomb, I mean interpretability bomb. I'm going to be dropping interpretability bombs throughout to motivate these sort of takeaways that hopefully stimulate some project ideas on your end. So I bomb number one, sheep happens. So if you look very closely to the tags that these two images have been given, you'll notice that, oh, they've been tagged as sheep. One of them has also been tagged by giraffe, and the other has been tagged as rainbow, but really we care about sheep here. So why, what is happening here? Well, to most of you, it should be fairly evident that, okay, you trained it on pictures of sheep, and so the sheep were always in some sort of grassy background, and so it's really learned to predict grass, but tagged it as sheep. And so this correlation has led to your model being confused about what is the real concept of sheep. So you want interpretability because you want to ask your model, okay, what is a sheep? And it should tell you that this is a sheep. I don't mean in a language sense, but highlighting in an image what pixels are activating the class sheep. So sheep happens, and then a downstream effect of this is if you take a sheep and pick it up in your hand, suddenly it turns into a dog. If you take orange colored sheep in a grassy valley, it turns into flowers. So there are multiple downstream effects of a simple lack of interpretability in your model's learning technique. So going back to like good explanations, why do we need them? Well, we need them for understanding what our model is doing. We need them for safety. We need them to make trade-offs between what classes we want to predict well on. We might not be doing better on other classes, and we want to understand these biases, which ties into ethics as well. But a crucial point is debugging your model. That's really like from an engineer's perspective. If you say, I don't care about the rest, well, at least you need to debug your model. And for that, interpretability is super important. So the question that comes up then is like, how do we measure the quality of explanations? Well, Finale Doshiwala, she's a researcher at Harvard, working quite extensively on interpretability. She says like good explanations turn out like porn. You know it when you see it, and it's hard to quantify. And a lot of people just treat interpretability as this atomic thing, this unit that you use to measure other things. But like no one has clearly defined this unit. Like there is no formal explanation for what interpretability is. My slides got mixed up. So if like in order to get at this formal definition, we need to start at least by like defining proper evaluation measures for interpretable AI. And there are multiple levels of these evaluation measures. One of them is application grounded evaluation, where your expert humans, for instance, your doctor, looks at these images and says, okay, is this really like an interpretable output of this model or not? The second sort of evaluation is human grounded, which means not necessarily experts, but at least real humans and some sort of proxy tasks that the model performs should reveal more about its decision making abilities. And when we don't have humans either, we want completely proxy measures. So like what sort of, is your car detecting pedestrians at all? Is it, how frequently is it detecting them, and those kind of things to actually serve as proxy as measures of safety, because that is a key part of like the decision making process. And yeah, so people start by defining two kinds of ways for implementing interpretability. One of them is like taking these models. So we've studied linear regression and like linear models very extensively, and we know that they are interpretable in the sense that their features make sense to us. Like there is a simple feature, there is a simple feature parameter learned for that particular, there's a model parameter learned for that particular feature. And we are saying this directly means that this feature is this beta important, is of beta importance to us. And that happens for on a per feature basis. So that is directly interpretable model. So which we call intrinsic interpretability. Your, for example, your binary decision trees, it's clear that there is a binary decision being made based on this feature, which has either it falls into less than a threshold, either it falls into above a threshold. Based on this, I'm making the decision. And at each stage, that is clear. And so that entire model is interpretable versus this set of techniques called post hoc, which is what we do after you actually training, you complete training your model and you arrive at this sort of uh, 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 inference task, and you're like, okay, but like now I want to interpret what this model is saying and why. And that post hoc techniques is involves things like making new predictions, changing your data a bit and seeing what the model says. And we'll get into the details later. But for now, this is what one of the segregations is like, and this professor at CMU, Zachary Chase Lipton, writes that, okay, but model based can really be divided into more clearer, more granular distinctions. One of them being the simulability of a model. So like, can we actually rebuild the entire model as a simulator and like interpret every aspect of it? So like a model level interpretation. Then there is decomposability. Can we divide this model into individual parts and say these parts are individually interpretable and they combine in some way to form this whole prediction? Or can we have this algorithm level interpretation? Like I can see per iteration how my a model is changing, like this interpretable training procedure. So that those are the three levels of transparency that he divides model based interpretability into. Well, I shouldn't say model based, I should say intrinsic um, interpretability. And the other is post hoc, like we saw before. Well, he and this is another I bomb that he drops. He says linear models are not strictly more interpretable than deep neural networks. Well, what does this mean? Well, so his hypothesis is no one's no, there are various definitions of how you measure interpretability, right? One of those is feature intelligibility, which means like, can you actually look at the feature and its importance and predict like what the model, how much value the model is associating with it? That is one measure of interpretability. That is also a big reason why we say linear models make more sense as interpretable models than deep neural networks. Well, but in this case, he defines and he cites his own paper, and it's a feedback loop, but there is some value to it in the sense that he is defining this missing data time series problem. So think of this as you want to classify patients. So you have multiple time series measurements of patients' vitals, and you want to classify, you want to put them into different buckets based on severity of disease. And he's saying that with linear models, in order to achieve a really good performance, you have to do complex hand engineering of these features. And there are missing points in the middle. So there are like these points at which you have no time, and your linear model has to learn on this time series and output a certain class label. And it doesn't do well without complex hand engineered features. Whereas your RNNs, you simply give it the time series and give it some 0, 1 values where the data is missing and where it is present. And it can actually do reasonably well with these things without all of this complex feature engineering. So if you go back and think about it, like you call linear models interpretable because your features are simple and you can interpret it. But in this case, you can't. Like your features are super complex and like it's not easy to interpret them. So in this case, like deep neural networks are evidently more interpretable than linear models. So you can create these sort of situations where you, yeah, I would say it's a hot take, but it has some truth to it. Um, Another way you can define your techniques is at the global level, so the model level, or like at a local level, at a local neighborhood of the data. You do some stuff and then you make predictions and you check what is happening there, or you fit a model to like predict in the locality of a particular data point, versus you look at collectively at your model learning on your data and identifying what level of what sort of interpretation that has. And with that, I'll get into some methods for interpretability. And this will be like probably like I also break down the math, but we don't have to get into that. So I can give you like an overview of what this is. So suppose you have your data set X and you divide them into two sets of divide them into features you're interested in and features like that, just the other features, right? So I'm interested in one or two features of like that I want to really interpret, and the rest of them I don't really care about right now. Or I can pick one or two at a time and build these plots. I say one or two because you ultimately want to build some sort of plot like this out of your features, and it's harder to do that with 4 or 5 features at a time, and you really can't. So if I pick some features at a time, what I'm saying is I marginalize my model over the rest of the features. So I basically want to evaluate my machine learning model, how evaluate how it how the predictions vary only with respect to these two features. And we've seen this marginalization before in these, I, yeah, I don't want to mention latent variable models and confuse people, but like there are some variables that you don't care about, and you say, okay, let's look at all the values like with respect to these variables and sum them out. Basically, that is marginalization. I feel like we've discussed this though. Um, so once you marginalize over the rest of your features, you are left with, so in this case, let me get my pointer. So your f hat is what you want to get. Your f would be your model. Your f hat is your estimate of the model's predictions with respect to these features of interest xs. And you want to get the expectation with respect to xc. So on average, with respect to all the other features, how does the model do on xs? That's a very hand wavy sense the math you want to do. And you do that with this idea, with the Monte Carlo estimate. You basically you have some samples, you calculate the average with respect to those samples, and you say, okay, they vary as per this plot. So here my features of interest, it's a cancer risk prediction problem. My y-axis is the number of pregnancies that a woman has gone through in her lifetime, and my x-axis is the age. And the reason partial dependence plots are nice is because now you can see these clear sections. So for instance, this section here says if you have between 3 and 12 pregnancies at an age between 0 to 20 years old, you have a slightly higher risk of cancer than if you have 1 or 2 pregnancies. And it's intuitive in the sense like you can just look at this plot and make out, okay, this is some sort of pattern in these predictions. Same for this group of people between 25 and 40 years old, 45 years old. You have a lower risk of pregnancy for women with all of the like this entire range of kids. But after 45, suddenly the risk of pregnancy increases quite a bit. So basically, the essence of this is you can start interpreting your predictions by visualizing the patterns in them. But there is one problem. When I considered this marginalization procedure, I'm saying I can divide my data set into features of interest and features that I'm not interested in right now, right? And marginalizing over these features that I'm not interested in means I am ignoring the fact that they might have interactions. And so that uncorrelatedness assumption results in a failure if like that doesn't hold for the data that I'm interested in. And because of that, the simple next step is to look at this thing, this conditional distribution of the features of interest. And again, I don't want to get too much into the math here, but the idea is this is a better model because in case your data is correlated, this will at least capture that conditional distribution as opposed to assuming that they are uncorrelated. And then there's a further next step. So the conditional distribution versus like this grid wise, so a binned distribution. So when you say conditional distribution of we spoke about two features, right? So x2 and x1, you want to examine the conditional distribution of x2 by fixing x1 to one value. But in your data set, you might not have enough of these. Yeah. You're on mute.
I'll have to drop off something
Yeah,
at the moment.
no
Yeah, but could you please send me the recording of your presentation?
Sounds good.
Thanks.
All right. Save. Cool. So this is like the conditional distribution. But a better way of modeling this might be to actually bin your x1 because I have some samples of x1 from different regimes over its support. I might not have the same thing for just one fixed value of x1 and like I might not have all of these value of x2 just because of database limitations. Excuse me. So binning them leads to a further another different technique that is a slightly better model. So like you see a pattern here, you're making more and more realistic model assumptions and creating this creating a new method of interpretability each time that does slightly better than the previous case. And the conditional technique is called M plots, and the binned conditional technique is called accumulated local effects. And so all of this, like I created a nice bibliography. So all of these methods with examples and all of that is in the bibliography. So don't worry about the links. But just pause. I will pause here in case like there was something that was unclear so far in the presentation, or if you generally have questions.
Swapnil, I had one doubt, maybe so in this case, like you are binning this thing, so like when we are binning also, like the data points would remain same, yeah? Like there's a on left side there are a lot of data points on right side. Like is it something like maybe I'm not able to follow or something? Like binning is just creating like the columns like or like different regions, but the data is going to be same. Like so, is this left and right different data, or like we are just projecting this data onto some like binning, but reducing like the
So all
columns?
of this is coming from the data set. I just copied that plot. So I don't think this is the exact same data, but
Okay.
the idea is highlighted as it's a better assumption to make that x1 will have some different ranges of values, and you want to bin those values and treat those averages like those conditional means, but it's still a better assumption to make than assuming a big fixing x1 and then observing all the different values of x2. Like you might not have enough samples to actually approximate that really well, right?
Okay. Yeah.
So that's why you're saying okay, instead of the naming is a bit weird, like they call it M plots, like marginal plots, whereas this is clearly a conditional distribution. But like the idea being like it's fixing one to a particular value and then looking at the marginal distribution of the other,
Okay.
which is really like a big ask, like saying that you will have enough samples to actually approximate the marginal distribution of x2 given x1. Sure, in the neural networks regime it might be fair, but like in typical linear regression problems with like the order of 100 samples, that's hard to say you can do very well, which is why this next model makes less assumptions. It says okay, at least within each bin I can have enough samples to approximate that conditional distribution.
Okay. And also, like in this doubt, like basically means, let's say if we consider like this joint plot or something like that, where we plot like the distribution of each individual like features, and then map out like the relationship between them. So like, is that thing or something like in more way interpretable, like combining these things, or like how does that, like does
So
that thing is more or less kind of in a way leading towards interpretability, like because in that case also we are kind of mapping out the relationship between two, like by finding out Pearson coefficient and all, like but yeah.
so a joint is a product of a marginal and a conditional. So I mean it essentially it is built up of these plots, which is why you want to go down to the lowest level and start from there. So like
Okay.
if you look at the joint, it will give you like the joint idea of like how they vary together, but it won't tell you how one varies with respect to the other,
Okay.
right? So for the joint, you take a joint, you draw a fixed line, and then you look at how the other varies, right? So this is the joint plot. Like what you're talking about is on the left, and like
Yeah.
now you're fixing x1 to 0.75 and seeing okay, for this value how does x2 vary,
Okay.
and you're saying now along this line I might not have enough points to see how x2 varies, so let's do one thing, let's take a couple of lines around it and then look at x2 varying about that bin, which is
Okay.
exactly what you're doing on the right here. So you're taking a bin and saying okay, between these things along this line how does the other one vary.
Okay. So like we have divided the region, and now like we are basically for x equal to 0.75, we are like looking for that particular bin and then finding out the variance like in terms of the data points.
Exactly. In fact, Z is called some sort of grid variable if you go and look at the
Okay.
explanation. So that's the
Okay.
idea.
Okay. Okay. And then I had posted something in chat, like basically kind of like
Ah,
the
sorry.
what was the reason for binning, like Can you go over it again? Like,
I missed the reason for binning. Is it possible to go over that again? Yeah, sure. So this entire the same idea, like, so these dots are representative of the joint distribution. Now you want to see how x2 varies with respect to x1. So you fix x1 to this value 0.75, right? Now along this line, x1 is always 0.75. So you want to see how x2 varies. But along this line, there are almost no points. Like this small black point is close, but like what other points are, oh shit, what other points are along that line? Almost none, right? So in order to make a better modeling decision, you decide to take a couple of lines. So can I draw? I cannot draw. But you take, oh, I cannot even click. You take this sort of grid, and then within that grid, you assume, okay, within this bin, I will fix a certain value for my Z variable, right? So I won't care about how x1 is varying. I will say that assume x1 is relatively like fixed within this small bin, but I will look at how x2 is varying within that bin. So very small changes in x1 and shows us like how x2 varies. And that's why this binning is a more realistic assumption in terms of like the number of samples you have. If you have infinite samples, it doesn't matter. You can always calculate the marginal. If you have infinite samples, you just want to do this, right? Well, not exactly, because that still doesn't say they are uncorrelated. They still might be correlated, but then with infinite samples, you can calculate those correlations, right? If you have two different functions, you can always calculate. You don't have to estimate anymore. Infinite samples means you have the true functions. So yeah, anyway, this is all like has to do with like in the limit of finite samples. How will you make better and better modeling assumptions that lead to less and less strong assumptions on your data? Yeah, so typically weaker assumptions are better. Anyway, that was a very mathy approach to visualizations and stuff. This is a much simpler idea. Global surrogates are essentially, say you have this problem of predicting how many bikes are rented on a daily basis. With some black box model, you have learned a very complex function. So say support vector machines. If you don't know what SVMs are, forget about it. It's just imagine it's a big neural network that you put your predictions through and put your data through and got some predictions out. And you want to fit a simpler global model to your predictions as opposed to the true labels. So you fit your black box model to the true labels. But now you fit your interpretable model, so your linear regression, to the predictions of your black box model. So because you want to see how the model is working, you don't care about like what actually happens with the data. Like this, the goal for this global interpretable model is just interpretability, not like good predictions. So the check on like is this global model doing well is to see how much variance is explained. So this R squared, and I don't know if we came across this in the Unicode reading group, but like the R squared is the explained variance of your data. So if your data is varying a lot, you want your model predictions to be able to capture that. So from a PCA perspective, like you want to, from a dimensionality reduction perspective, you want to reduce your 50 dimensional data to 5 dimensions, but you want to be able to explain the variance very well with those 5 dimensions. You don't want it to be like a tiny 5-dimensional box, whereas your data is actually huge and varying a lot in every dimension. So yeah, so R square is this metric that tells you how much variance in your data have you been able to explain with this simpler version of it. And so the same definition holds in this case. You want to use your globally interpretable model as a surrogate, and a surrogate is a term for like a proxy, like a surrogate mom, um, um, as a, yeah, to explain your black box model. And here's an example of the same. So in this bike rental prediction problem, what it turns, so there are two features that we care about: days since 2011 and the temperature. So if days are less than 435, so maybe like we're in 2013, and the temperature is less than 13, there are like say 2,500 or 3,000 bikes rented. However, now if we look at the same time, like around 2013, but a temperature that is greater than 13, now this prediction average increases. So with increasing temperature, people rent more bikes, which makes sense. But it wasn't as clear from the black box model's predictions. It happened after we fit like this set of trees to this model with decision tree. Same for days greater than 435. Less temperature is clearly indicative of like less bikes rented. Yeah, that's all I want to say. Now we've spoken of these global level surrogates, but like sometimes when your black box models are super complicated, a global surrogate can't necessarily capture all of these explanations with like well. Like it can capture the explanations, but it might not do that well. So what can we do to improve this? Well, we can use local surrogates. And what local surrogates means is, forget this equation, I'll get back to it. Look at this slide. Um, so in slide A, in picture A here, you're basically training your black box model and arriving at this decision boundary for a two-class classification problem, right? And this is your data set. Let's say you're interested in this yellow point, right? What can you do? Well, you have the black box model. So just take that model, perturb the data, or maybe weight the data around it really high. So pick data points that are near it, weight them really high, and like train the classifier to predict on those. So obtain those predictions. And in order to get like this local decision boundary. So find a local point, find points around that local point, put them through the classifier, figure out what the predictions are nearby, weigh them higher, and train a locally interpretable model to make those predictions. So in essence, like now you switch from that global interpretable model to like this locally interpretable model where around your data point of interest, you're able to tell what your black box model is predicting. And that is a really popular approach. Lime took off quite a bit when it was launched. I don't know how much it's used right now. But yeah, so that was Lime. The math behind Lime is in this slide. I don't think it's super complicated to go through. But what you're saying is you're minimizing some sort of loss function over your black box model, your family of possible explanations, because you're choosing a model from the linear family, and you're choosing a proximity measure for how close you want to be to your data. And there is this additional term, which is like this model complexity, which depends on the number of features you want to be able to explain. And all of this, remember that we keep saying like one feature, two features, like couple of features. So explainability tends to have this notion of like you want to explain a few things at a time. And it makes sense, like for the plots, you definitely can't see like a 5-dimensional plot. um, Forget interpreting, it's not possible to plot it. So it's hard like to do these things for at scale, which might be something you want to consider if you're interested in approaching those topics. But anyway, this is Lime. Another very popular approach has to deal with these Shapley values. So what are Shapley values? Well, you frame your prediction task as a game. And by this, I mean, games have some combinations of resources that you attach certain scores to. So in chess, a certain position might have a favorability for black and white, and there is a certain score attached to probability of winning, right? Similarly, like you treat all your features as these resources and you calculate coalitions of resources that you associate a score for. So to take an example, if you have some features like you have with respect to this feature of, oh man, I'm missing an image here. Okay, I'm talking about pets here. So consider the feature of interest as pets being banned in an apartment. and my prediction task is like the cost of the apartment. So I want to examine how much the pets being banned in an apartment affects the cost of the apartment. And so what I'm showing here in this slide is like what possible combinations of features can I create. I have three other features: park nearby, area 50, and floor second. And so I can create like at least 8 combinations, like 2 raised to 3, that your simple permutation and combinations, 8 different combinations of features. Um, in addition to, and now all of these you can add or remove the cats or pets band concept, and you calculate your values for each of these coalitions to your with respect to your pets band. And what this Shapley value is saying that is the prediction for this instance minus average of prediction for other instances. So if I want to check how much value a pets being banned has with respect to having park nearby, then I consider this instance with respect to an average over all other instances. So what is its average contribution to the coalitions versus what is the contribution in this instance? And that allows you to interpret this instance wise importance. And this method was extended to a bunch of different fields and like in a bunch of different models. So there was tree shap, there was shap itself, which was based on Shapley values. But like not getting into the math there, but rather giving you an intuition of like how, for instance, would this work in the image domain. So in image you have different features, right, created from these pixel level aggregations. So removing or adding a feature might correspond to removing or adding this face, for example. So that sort of translates to these other domains. So that is the idea here. This is just like the math behind it. So your Z prime is your coalition vector. So it's a vector of zeros and ones. So you have m items total. Each item has a 0 or 1, just like a representation of a coalition. So that you want to, this is like your optimization problem. And then you want to find this phi, which is the contribution of feature with respect to each coalition. Yeah. We spoke about line. So, okay, so now there is this class of perturbation-based methods. And we've discussed this actually in the reading group quite a bit, where you make two internal mistakes and they cancel out. And you end up with a nice classifier, and you end up saying, oh, this is a nice classifier, but you forget that that might have been because you just made two wrong modeling choices that balanced each other out. So it's the same concept here. All that is equal is not fair. Just because you do equally well on two different classes does not mean you're being fair about them. For instance, we just spoke about sheep, and if you're predicting sheep with as much accuracy as you're predicting dogs, but you're really just learning the grass, then you're not predicting sheep, you're predicting grass. So fair and equal are two disjoint concepts. There is a certain relationship, but all of that is subject to your interpretable machine learning predictions, subject to your being able to interpret the predictions. So this paper that these guys wrote, Kalhotra et al., they introduced this tool called Themis. What this does at a very high level is it creates these test cases. So when you give it a model, you give it some data, it starts perturbing the data, and you give it some features you're interested in. Okay, I want to test race and gender and how they affect your model predictions. It perturbs these data. So I change race until I realize, like, all else being equal, if I change race from Caucasian to brown man, with only this race flip, my prediction flips, which means it is super sensitive to this race feature. That same for gender, man, woman, trans, LGBTQ, whatever. Like all else being equal, if your prediction flips with one of these features being flipped, then it is super sensitive to them. And it calculates that confidence interval by all features are not categorical, they're actually numerical. So you want to vary them within certain ranges and then obtain certain confidence intervals and standard errors for what your method is doing. So that's what they did. with respect to a financial decision making set of tools, where typically you want to answer why a loan was denied. So, and a bunch of these tools actually said we are fair. So you definitely want tests for fairness more than they themselves created in order to like independently verify how fair they were. And they found that quite a bit of several of the tools are not fair. So I described the algorithm that they've actually given, and it's you. Yeah, we can read through this because it's fairly straightforward. Given a software S and a subset of its input characteristics, X prime, causal discrimination, their algorithm returns d sub x prime of S, the causal discrimination score with respect to x prime, the set of features that you're interested in, with confidence error and error margin. They say causal because they adopt this paradigm of all else being equal. If I switch this feature with a different value, then it flips the prediction, which is why they say causal. So like we haven't gotten into causal inference yet, but it's this idea of no unobserved confounders. Um, but anyway, like it's saying that there is nothing external affecting this process under that assumption. This is causal, which means like the fact that the salary is low is because I flipped man to woman, which is a bias that is often found and even today exists very widely in tech at least. Discrimination search is just an additional idea where if you don't know what features you're interested in, it does this search for you on its own. So yeah, it finds this X prime for you, given a certain interval that you're interested in, like which feature varies the most or which feature is sensitive. Okay, last set of techniques, which is related to gradient-wise methods. And this is super interesting because all of you trained a neural network at some point and you used gradients, and there is a simple approach to like using gradients for interpretability. The question these guys wanted to answer was which pixels contribute to what extent to a positive or a negative classification result. And these folks said if you have X, which is d-dimensional input to a neural network with C, capital C output neurons, so capital C classes, then let's say SC of X is the output for class C. So you have a whole neural network. The last set of neurons, you have 10 neurons for, let's say, MNIST classification, 0 to 9. And each neuron corresponds to a certain class. So I take the output of the last neuron for a certain prediction. And I want to say what was the contribution of each individual feature to this neuron. How do I do that? Well, it passes through a bunch of layers, right? So I simulate the backward distribution. So I go from like, I have a piece of cake I have a big cake at the end, and I want to go back and distribute piecewise slices to people who helped me predict this class. That is what I'm doing. And by people, I mean neurons and features. So I think it is fair to get into the math here, but let's look at a picture before that. The image basically says this is a sum of a prediction is a sum of feature relevances, which is a sum of pixel relevances. Okay, and I'm sorry for the background noise if there's any. Um, so you want to distribute your output over your feature relevances up till the point where you can calculate your pixel relevances. And that allows you to go back and model this layer wise relevance score. And so this is like the simple idea, like if I is the target unit of interest. So say you're interested in the last layer, the Cth class, then this I turns into C. And that is the relevance at of the Cth class at the capital Lth layer. L is the last layer, capital L. And so you start there, and then as you go backwards, the layers before it, you consider that relevance score of the last layer, and you weight that by the contribution of the outputs of all the neurons that are connected to it. Remember that there might be dropout and stuff like that. So not all neurons are fully connected. Not all layers are fully connected, right? So you pick which neurons contributed to it, sum their outputs and divide that by the total outputs. And you do that at each layer. So you go backwards from the end to the beginning by dividing your layer wise relevance across this entire set of outputs. And so that gives you this um, layer wise relevance score that they use to interpret what neurons contribute to a particular output. An extension of this is this idea of deep lift, which says, okay, but like what if I want to compare this with like this reference output? So a reference could just be an average of what happens across all classes, or it could be a specific example against which you want to compare all of the rest. So it might be a special patient versus which you want to see like, okay, how are the others doing? It might just be an average of all the patients versus which you want to see how one patient is doing. And so like either way, you can frame the problem, but like you need a baseline or a reference, and then we do the same layer wise relevance propagation stuff, except like now you're comparing it with one example or an average across examples or a class of examples versus which like you want to compare the rest. So again, the framing is up to you, it seems to me. um Practically, like this grad LRP, like layer wise relevance propagation, is basically just like these couple of lines of code, and then you get these gradients and you play around with them. So you really can create your own techniques. So what is happening here? So your TensorFlow and your PyTorch are frameworks that are structured in such a way that there are certain callbacks that happen. So you register these hooks where whenever it calculates a gradient, this function is called. That's what this register hook is doing. So it's like saying whenever your message comes to you on Facebook, a notification pops up. That's because the notification has a hook to this message. So your grad LRP has a hook to your gradient calculation or your back propagation, which means each time you just calculate your gradient, store it somewhere, do something with it, or do something later. And this allows you to track the progress of your classifier. So that's another like interesting set of like ideas that you can use to understand your neural network dynamics. And you can do these for very small neural networks. In fact, it would be nicer to do them for like tiny connets or like MNIST level neural networks where you really want to understand the dynamics where you don't have complicated data, because that's an added layer of complexity. So maybe do it for new architectures like graph neural networks. What are the dynamics of training on a very simple prediction task? So bottom line, like there are lots of things you can do. And the final idea I'm going to close with is this idea of sparsification. So the motivation is like even in humans, when you grow from like a baby to an adult, your neural networks first increase in density in terms of their synapses, and then they decrease, like they prune those some connections out. And I assume this connects with the fact that the number of gray cells you have are constant, like you don't generate more gray matter in your brain. But that's an aside. This is just about synaptic pruning at this point. And I don't think the field was motivated by this, the field of model pruning or weight pruning, fine. I don't think the field was motivated by this so much as it was motivated by smaller devices and like compressing models for the phone and mobile and stuff like that, or like just from a computational perspective. But it is nice to see that there is biological inspiration for model pruning. And so this is the general idea, like sparsity implies that by the end of the training, your model has only 10% of the weights it started with, right? And there are different ways of doing this. You can drop weights during training. You can train and then drop selective weights that are more sensitive. You can start with a fully trained architecture and retrain while dropping some weights. So that's up to you. And there is a lot of literature. And I would point you to Sarah's slides because she's been kind enough to send them to me. She has a bunch of work on like model pruning and like what this means. And one of the key takeaways there is it seems a lot of the weights in your very complex neural networks are used to learn the long tail of the data distribution. So if you have like 500 images of ones and twos and only 10 images of like 5, 6, 7, 8, 9, you're going to spend a lot of your weights learning these few images as compared to the ones and the zeros. So the more data you have, the less weight you spend learning them, it seems. Or the modes of the data distribution is where you spend most of your where you spend the least weights. Sorry. So when you prune away these weights, you still do well on these data where you have a lot of examples, but you don't do well on the rest of these. So which also leads to this line of work saying your sparsity amplifies the biases in your neural network. So if I already have less images of people from a certain demographic, and I'm learning these images based on a certain data set, and I'm going to prune that data set before deploying it to my mobile device, then I'm going to going to prune that model before deploying that to my mobile device, then I'm going to do bad on those demographies where I didn't have much data to begin with. So yeah, that leads to bias and ethics in AI, which is also um, one of the focuses of Sarah's work. Yeah, I want to add one. Like this is a long like line of work, but like one of the slides that stood out as like standalone that could be explained in a standalone fashion was this like pruning identified exemplars. So the idea I said about this mode of data distribution and long tail of images not being learned well, this is like the I guess the quantification of it. So these exemplars are images where the big model, the uncompressed models actually do well, but like the minute you start compressing, it starts doing worse on it. So for instance, this image was actually a gown for the true model, for the uncompressed model, and it quickly turned into plastic bag um, for the compressed model. So like what's happening, what's going on, and more importantly, how do we use this knowledge to do better? So that's this. I'm just going to leave you with this idea of pruning identified exemplars. And again, I'll share her slides so that you can at least see. She's actually given a bunch of presentations which are already online. So I double checked that these are public slides. But yeah, that's about it for me. I'm happy to take questions.
How does I didn't understand the like how does pruning come into the entire interpretability scenario?
Oh,
Like
that's I skipped the motivation here. I spent so much time on it yesterday. I was just like, oh man. Okay, so it doesn't necessarily tie in terms of like interpreting methods. It ties in more with like failures of existing methods, like identifying where existing methods fail, and how these examples might actually help us learn more about what we're doing with these over parameterized neural networks. So you're right, like I wanted to treat model compression entirely separately, but like it's something that you guys can actually work on in a practical sense. Like you have all of these complicated models pre-trained available, so can you not like play around with those? For example, in NLP you have Hugging Face that gives you a bunch of pre-trained models, and like pruning is not like computation intensive, because all you have to do is perform inference on the data set, prune, perform inference, and figure out what is going on. Maybe transfer learning might help, but like it's not like complete retraining. So I wanted to just mention that as an aside. But yeah, you're right. Like it's not. I don't see the clear thread tying those together, but I think it is a very cool area, so I added it anyway. Other
Like
questions?
maybe kind of I can say like in a way pruning this helps us understand like kind of like how important like does that weight or layer like we remove like plays in terms of like the means it's similar to like I can say dysentery only like they have also like this way so we remove some feature we try to understand how it does and like and when we again add it like something related to
Your voice just trailed off in the end.
so like I'm saying maybe it's something like which can kind of in a way like decision tree only. Like, so we take some features, like we remove it, try to understand like how removing that feature like basically affects like the actual prediction in a way. So based on that, like how it affects the actual interpretation, or like the uh, basically like let's say if we're thinking of convolution layer, so like in terms of convolution layer, how it affects the like predicting the smaller level features, like
So pruning plus what you're talking about is actually perturbation initially, like removing features would be perturbation. I would be interested in seeing how pruning and perturbation go together. So removing features and removing weights, like does that, can you counterbalance the effects? I don't know, that seems interesting.
but like
I,
in a way removing features are like, we are just like if you see for neural networks, if we are considering like that way, just similar to a pruning only, basically we are like removing the like some weighted features like that way. We are not considering that thing, like especially in terms of neural networks, or it's
are
something
you
different.
talking about features or are you talking about feature maps? Because feature maps have to do with weights. Uh, not.
Yeah, feature
Oh,
maps, sorry.
yeah, yeah. So okay, yeah. Then that's pruning. Okay, got it.
Because like in terms of neural networks, if we see like we don't know like what kind of like features there would be, like basically we have like a lot of nestings, like so maybe like kind of like to understand like which features to take, which features to not take, like that way. So we have to go.
Yeah, I think one technique that I didn't mention here, something called grad cam, which is visualizing the heat maps or the activation maps generated by these data when they pass through the neural network. That is a super interesting line of work, but it's just been overused in medicine, according to a friend of mine who's like this MD PhD student. So he's like, I'm tired of grad cam in the sense like doctors are tired of them as well. So I didn't. I should have added it. In all fairness, it's probably a really popular method that I didn't look as close into. So I am biased by my perspective, but the idea was just to give you folks an idea of like these are some directions. Go out there, find out what you want to do.
Yeah.
Cool. If there are no other questions, I should stop recording first.